Alrighty, folks, it is time for lesson 2, differential equations. So let's first make sure we know what a differential equation is. You probably have an idea that it has something to do with differentiating and equations. And you would be right. A differential equation is an equation that involves a function and one or more of its derivatives. So solving a differential equation means determining the specific function that satisfies not only the derivative, but all of the given conditions. If you're like, I still have no idea what any of that means, Ms. Neufeld, no worries. I find it makes more sense when you just do an example. So let's do example 1, shall we? Determine the equation of the curve y is equal to f of x, which passes through the point p0, 2, such that f prime of x is 6x squared plus x minus 5. In other words, they're giving us the derivative, and they want the original function at that particular point. So, given a particular point. So, basically what we're doing is to get f of x, we need to take the antiderivative, or the integral, of f prime of x. If we take the antiderivative of the derivative, we'll get the original function. So what we have is that f of x must be equal to the integral of 2x cubed plus, oh dear, I'm giving away the answer. Don't look, it's a secret. Of 6x squared plus x minus 5 dx, which, again, I'm going to start loosening up on showing all of those antiderivative steps, but which should be, if we do our work right, this should be 6x cubed divided by 3, so we added one exponent and then added 1 to the exponent and divided by that exponent, plus, again, same idea, it's going to be x squared over 2 minus 5x plus c. Don't forget about our constant. Then if I simplify this, this is just 2x cubed plus 1/2 x squared minus 5x plus c. Okay, but I'm not done because they've given us more conditions than that. We've got the point 0, 2. So what that tells me is that I have been given that x is equal to 0 and f of x is equal to 2, given that point. So we can rewrite this equation as 2 is equal to 2 times 0 cubed plus 1/2 0 squared minus 5 times 0 plus c. And with a little bit of incredible mathematics, we can determine that c must be equal to 2. So before, when we had the antiderivative, we just left that c alone. We're like, hey, yeah, here's the c. It's some constant. In here, there's one specific constant that will satisfy all of our conditions. So this tells us that the function that satisfies all the conditions that have been laid out is f of x is equal to 2x cubed plus 1/2, ooh, that was weird, x squared minus 5x plus 2. We're just replacing that c value with a 2. And that is solving a differential equation. So again, the big difference is this time we just need to solve for what c is. That's really what makes this different than what we did in the past. And if we check our work, we could easily take the derivative of this and get back to the beginning. And we can also tell that this equation does go through the point 0, 2. All right, tries. Remember for these, I want you to try them on your own first. And then, you can come and watch the video if you get stuck. So, first thing, I'm just going to rewrite f prime of x in a slightly nicer fashion. I'm going to rewrite this as 3x to the 1/2 minus x to the negative 1/2. So I'm just going to write those ones as rational exponents. So that means that f of x is equal to the antiderivative of 3x to the 1/2 minus x to the negative 1/2 dx, which is equal to, okay, I'm just going to use the same patterns that we've done before. If I add 1/2 plus 1, that's 3/2. So it's going to be x to the 3/2. And we're going to be dividing that by 2/3. Man, my pen is really laggy right now. I'm sorry about that. And if we add 1 to negative 1/2, we get x to the positive 1/2 divided by 1/2. And, of course, we have to add a c. Simplifying this one a little bit, just to make it a little bit nicer, we get 2x to the 3/2 minus 2x to the 1/2 plus c. Now we take our conditions. So if we look at our conditions, we have f of 1 is equal to 2. So f of x is 2, x is 1. So we get that 2 is equal to 2 times 1 to the 3/2 minus 2 times 1 to the 1/2 plus some value of c. Nice, all of those rational exponents don't really hurt us because it's 1 as the base, which is really convenient for us. 2 is equal to 2 minus 2 plus c. Oh, well, that's just dandy. C is equal to 2. Convenient. Therefore, we get that our f of x must be equal to 2. I'm going to rewrite this as the square root of x cubed. I don't have to. I could have left it as x to the 3/2. I just felt like writing it as radicals. 2 square root of x plus my constant, which is 2. All right. Next one. F prime of x is equal to 3 cosine x plus 5 sine x when f of 0 is equal to 4. So we know that f of x is going to be equal to the integral of 3 cosine of x plus 5 sine of x dx, which means f of x is going to be equal to, all right, so we're working backwards again. We know that the antiderivative of cos x is sine x, so this is going to be 3 sine of x. We know that the antiderivative of sine x is negative cos x, so this is going to be plus 5 times negative cos of x plus c, or just 3 sine x plus, I stand by that one, minus 5 cosine x plus c. But we have some conditions. X is 0 and y is 4. So we get 4 is equal to 3 sine of 0 minus 5 cosine of 0 plus c. But sine of 0 is just 0. So it's going to be 3 times 0 minus 5 times 1 plus c. And if we solve for c, we'll get that c is actually equal to 9. Right? We just move that over, add the 5 to the other side, and we'll get 9. So that tells us that our f of x is then 3 sine of x minus 5 cosine of x plus 9. And this leggy pen is really bothering me, so I'm going to go fix that. So just wait, except you don't really have to, because I'm obviously going to edit this so that it moves synchronously to the next page without you actually having to wait, except for the fact that I'm talking about it, which makes you have to wait. Thanks for waiting. I'm back and my pen is all fixed. So I have example 2. Find f if f double prime of x is equal to 12x squared plus 6x minus 4 when f of 0 equals 4 and f of 1 equals 1. Okay, you might notice something here. They have given me 2 conditions. There might be a reason for that. Also note that they've given us the second derivative, not the first derivative. So what that tells us is we need to take the antiderivative twice. We're going to need to do it twice to get back to f of x. So we'll start by finding f prime of x. So f prime of x is going to be the antiderivative of 12x squared plus 6x minus 4 dx, which is equal to, okay, we just work backwards. This is going to be equal to 12x cubed over 3 plus 6x squared over 2 minus 4x plus c. I'm going to call this c1, because if I'm going to be taking this antiderivative twice, you better believe there's going to be more than one constant that's going to pop up in here. So I'm going to call this c1. So if I simplify this, of course, it becomes 4x cubed plus 3x squared minus 4x plus c1. Okay, now, if I take the antiderivative again, if I want to find f of x, that's just going to be the antiderivative of what I've got here, which is 4x cubed plus 3x squared minus 4x plus c1 dx. So the antiderivative there is going to be 4x to the power of 4 over 4 plus 3x cubed over 3 minus 4x squared over 2. Man, these are working out real nice. Plus c1 times x, right? Because the antiderivative of a constant is that constant times x, plus another constant. Okay? So, here's what I'm going to do now. Now, I need to solve for both of these constants. I could have done them one at a time, but I don't want to. So this simplifies to x to the power of 4 plus x cubed minus 2x squared plus c1x plus c2. Whew, okay. All right, now we're going to be solving for each of our c1 and our c2 one at a time using our conditions. So I'll start where f of 0 is equal to 4. So what that lets me do is I can say 4 is equal to 0 to the power of 4 plus 0 to the power of 3 minus 2 times 0 to the power of 2 plus c1 times 0 plus c2. You'll notice what this does is this basically allows us to eliminate everything except for c2. How convenient. So we've got our c2 is equal to 4. Actually, that bothers me. I'm going to write it the other way. Yes, honey, I know it's all very exciting, but I need you to be quiet. I'm busy. So c2 is equal to 4. That's what we got out of our first condition that we were given. But now we need to solve for c1. So we haven't got c1 yet, so we're going to have to go back to our equation. And this time we're going to use our second condition, which is that when x is 1, that's the same highlighter. It was supposed to change, and it didn't. When x is 1, y is 1. She is not going to be quiet. All right, 1 then is equal to 1 to the power of 4 plus 1 cubed minus 2 times 1 squared plus c1 times 1. Now, c2 we've already solved for. It's 4, so we can just throw that in there to solve for our c1. What we get is 1 is equal to 1 plus 1 minus 2 plus c1 plus 4. And when we simplify that all down, we get that c1 is equal to negative 3. Now that we have both of our constants, we can finish this thing. So, f of x is therefore equal to x to the power of 4 plus x cubed minus 2x squared plus, well, I should say minus 3, so that's throwing in my c1, minus 3x plus 4, my c2. And that is the solution to our differential equation. Okay, we've only got one more example. This is a try, so again, give it a shot yourself before seeing how I do it. But suppose for the graph g that at every point dy dx is equal to 3e to the negative x. So at every point the derivative will be 3e to the negative x. Find an equation of a graph that is parallel to g but passes through the point 0, negative 5. So parallel to g means that at every point along the graph, along both graphs, their tangent lines have the same slopes, right? In other words, they've just taken the graph and shifted it. The equation we're looking for is a graph like g, but just shifted. So what we're looking for then is we want something that would have the same derivative. It would have the same slopes, meaning it would always have the same derivative. If it is parallel to g, then it has the same derivative, because it means that all of its slopes should be the same. All of its tangent lines should have the same slope. So what we need to do is we need to find a y such that dy dx is 3e to the negative x. So what I'm going to get is that y is equal to the antiderivative of 3e to the negative x. So what that gives me is 3 times 1 over negative 1 e to the negative x. That's our antiderivative for e to the negative x. We've done that one before. Plus some constant c. But we've been told specifically that x is equal to 0 and y is equal to negative 5 at some point along this graph. G doesn't have to go through 0, negative 5, but our equation does. So we set that condition. Y is negative 5 and x is 0. I didn't simplify that equation before. I'm going to do that real quick. So I should have. Whoops. There we go. Now we say that x is 0 and y is 5. Back to where we were at. So now I set y to negative 5, and I replace my x with 0, e to the negative 0 plus c. But e to the negative 0 is the same thing as, what's negative 0? There's no negative 0. E to the negative 0 is this, you could hear the quotation marks, right? The negative 0. E to the negative 0 is the same thing as anything to the power of 0, which is to say that it's just 1. So if we finish this off, we get that c must be equal to negative 2, which means our final answer, the equation that is parallel to g and goes through 0, negative 5, is negative 3 e to the negative x minus 2. This equation is parallel to g and goes through 0, negative 5. Bada boom. And there we go. We're all done with differential equations. Go do some homework. Learn. Be free, but like not actually free. Like math free. I don't know what that means. I should cut that out of the video.